Okay, morning everyone. I've tried my best to build the course for the most part around this somewhat interesting definition of structural engineering. And so far, we've spent a little bit of time talking about the materials we don't really understand. In lecture 2, we talked about structural steel, how it's made, and some of the uncertainty that we may find in the geometry and the yield stress. Into shapes we can't really analyze. We talked a little bit about structural forms over the last couple of lectures. We talked about gravity framing, how it's arranged to support the loads acting on the structure. And we talked about bracing and braced frames in steel buildings, then the role of those braced frames in supporting lateral loads applied to the structure through things like wind and earthquake loads. And now we're getting into the part of the course where we're talking about how to design these structures to withstand forces we cannot really assess. Okay, so we're going to spend lectures 5, 6, 7, 8, and 9 talking about the source of loads acting on our structures and what we do as engineers to estimate what those loads might be. And this includes gravity loads. We're going to talk about dead, live, and snow loads. It includes wind. So we're going to talk, or lateral loads. So we're going to talk about wind and earthquake loading. And there are also some lateral effects that we need to consider from the gravity loads, which seems strange at first, but we'll go through that in lecture 9. Okay, so today we're going to start talking about these forces that we can't really assess. And the reason we can't really assess them is because just like the resistance, perhaps, of a steel member, it has some inherent variability. We calculate a value, but we know that there's some uncertainty around that value. And for loads as well, which are denoted here in the S curve, we're going to calculate a value, but there's some inherent uncertainty around those values. Okay, so we're going to talk about what kinds of loads we have acting on our structure, and I'll give you a sense for their variability about the value that we're calculating. And all these loads are going to come from Division B, Part 4 of the National Building Code of Canada. Okay, so this is the first day we're really getting into NBC stuff. We're going to start talking in the labs, and we've actually talked a little bit over the last couple of days about how we might be able to do some structural analysis for the loads that we're going to be calculating. We're also going to spend some time in lab running structural analysis using STAAD.Pro software. And once we wrap up the part where we're calculating loads, the rest of the course is going to be spent talking about the resistance side. So I talked very, very, very briefly about like if we wanted to estimate the yield load of a brace or something like that. We could do AFY and calculate the uncertainty around it. But there's a lot of other things that we need to consider as well, and that's what the rest of the course is going to be on. So today is on introducing components of the NBC, the loads we need to design for. And we're going to focus today on dead and live loads. And these all come from Part 4, Division B, or Division B, Part 4. Specifically, Section 4.1.4. Go to the PDF document, go find Section 4.1.4 and 4.1.5. They're dead and live loads, respectively. I'm not going to read the code to you verbatim. I'm going to give you the highlights, the important things that we're going to focus on in the course, but it's up to you to go and actually read the stuff that's there. Okay, you want to know what the code says. Otherwise, you're going to miss something, make a mistake, and be held legally responsible for it. The way that Part 4 is organized is basically in this manner. We've got 4.1, which is structural loads, and we're going to have 4.1.4 for dead, 4.1.5 for live loads, 4.1.6 for snow and rain, 4.1.7 for wind, and 4.1.8 for earthquake loads. We're going to talk about each of these things, and today we're going to focus on these dead and live loads. After today, you should be able to describe the types of dead loads and live loads we might need to consider in a building, and describe their bias and variability as we did for the tension resistance of a member in lecture 2. Should be able to identify and tabulate design dead loads acting on the floor of a building. So once you're able to describe the types of dead loads, we actually need to quantify them. Live loads are a bit simpler. All you really need to do is go and select an appropriate live load value for the building based on the occupancy. Occupancy means what is the building used for. This is a classroom, so the occupancy for this room would be classroom, and there's a load that we have to design for live loads in classrooms, and we're going to look those up in the table in the building code. And we're going to see that if we just take the live load from the table, use it everywhere, there's going to be a lot of people in the building, and I'll give you an example of that. And it's a little unreasonable. So once we get to the point where we have a member that's carrying a whole lot of floor space, we're going to talk about how tributary area factors into this. You should be able to determine what's called a live load reduction factor for the member that's supporting those floors. I'll give you some context for what that means. Does anyone have any questions about these three items or anything else that I've talked about so far before we get into the material this morning? Okay. Poll everywhere question. Open your phones, open your laptops, whatever. I'm asking you to think a little bit about what things you might consider as a dead load in a building. Look around you, think about rooms you've been in before, buildings you've been in before, the things that you see. What types of things in a building do you think should be lumped into this category of dead load? It's a word cloud problem. Basically, you're asked to type in some words. So we've got weight. I'm sure it's probably structure weight, I'd imagine. So weight is obviously going to be important. It is a kind of gravity load. Everything that the gravitational forces pull down towards the center of the earth is going to be acting on the structure, so weight's important. We've got students. Depends on how lively you might be in the classroom. I might consider you a dead load if you're sleeping on the table. So we've got walls, slab, stationary. That would be a pretty small dead load, but something for sure. Self, material, structure, objects. Some of these words might be getting split up. Permanent is a fantastic word. Whoever put permanent, I like that word. Everything that we're going to be considering as dead load is essentially going to be what's called a permanent fixture. You might have read in the slide somewhere, permanent fixtures, if those are the two words that you put in together. So the words that come up here that I like to do this exercise because there are a couple misconceptions. Furniture, the first thing that might come to mind is an inanimate object, right? Something that's not alive. The tables don't walk around, they're not alive. They're an inanimate object, right? But they're not permanent. I could take this table, as I often do here, and I can move it from there to here. A live load is going to be anything that can change in position with time. That includes people, that includes storage, that includes furniture, anything that's not a permanent fixture of the structure. Lots of other good words up here, though. We've got the self-weight of things, if I were to put some words together, of beams, of slabs, of walls. Permanent fixtures is really the important thing there. Anything that's part of the construction of a building, that's a permanent fixture. That would include floor tiles. I mean, in 20 years' time, you might rip it up and put down a new floor, but 20 years is pretty permanent, relatively speaking. Walls of structures are permanent. We've got lighting, right? We've got lighting, the electrical utilities that feed the lighting. We've got plumbing utilities. We've got HVAC. We've got a whole bunch of mechanical and electrical systems that we don't think about as structural engineers as often as we should maybe. And so there's a bunch of stuff hidden in the ceilings here that adds to the dead load as a permanent fixture of the structure that makes up its final form. Snow is not going to be a dead load. It is a gravity load. It ebbs and flows. It melts and snows. That's going to be a separate category of load that we're going to talk about later on in the course. In fact, next day. So that's fun. Another quick one here. You're sitting in this classroom at the moment. I think the capacity of this classroom might be 50 students. I'm actually surprised at how many of you are still here. That's pretty encouraging. Look around the room. Think about how many chairs are here, how many people are here. Approximately how many people do you think that this floor space would be designed for? If you were the structural engineer and you're going to look up a load that corresponded to perhaps the number of average weight people in the room, how many people do you think the floor of this room should be designed for? So that's starting to stabilize-ish. It's always funny, you can change your answer, and so from time to time you're like, oh yeah, that actually sounds like a better answer than this, or that sounds like a better answer. Who picked 100? A. Anyone want to raise it? You want to share why? Like what you thought about when you were thinking 100 seems reasonable?
Because I think you said the capacity was 50 for this class.
Mm-hmm.
So to me, if you are designing for double what the capacity is, it seems adequate to withstand the load.
That's very reasonable, isn't it? Because not only are we going to double it for 200 people, we're also going to apply load factors later, and we're going to talk about why that is. Now, that's not actually the right answer, which might be surprising. And I usually put that there because most logical people would think, capacity is 50, double it, that sounds reasonable. Maybe you have people standing or whatever in the space. So 100 is not the right answer. B, 350. Who picked B? Want to share your reasoning why you picked B?
Well, a doubling of the factor didn't seem like a good factor of safety. This room could probably pack in around 80 people, so approximately factor of safety around 3 is typically what I think that we go for.
Mm-hmm.
That's why I chose 350.
Perfectly reasonable, right? That's not the right answer, okay? If you were to design an attic space that no one ever goes in, or a residential, I guess, if this was a residential space, this was an apartment building, 350 would be about the right number, roughly speaking, for this space. Who picked C, 440? Want to share why you picked that?
This room is 15 by 10, so it will sum up to an area about 150 square meters. 3 people in each square meter, it would end up roughly 400.
That's a fantastic answer, and that's actually the right answer. Okay, so 400. I'm not grading this, right? So that's why I love that. So C is the right answer here, and what we're going to see, and that's actually pretty much exactly right. I had it, my old research supervisor, when he taught a similar course, used to tape a 1 meter square box on the floor. And a 1 meter square box on the floor is about 3 tiles by 3 tiles here, roughly. I mean, that's about a yard squared. But if you were to have one person and you were to pack 3 people into this little square of 3 tiles by 3 tiles, that's 3 people per square meter. The equivalent of that is 2.4 kPa. It's actually 50 pounds a square foot is where the number came from. So on average, spaces like classrooms or office spaces, the live load is essentially approximately equal to 3 people per square meter. Would you feel very comfortable in here at 3 people per square meter? That's a lot of people. I wouldn't feel very comfortable either. I've got lots of space up here, and sometimes I feel uncomfortable. Now, this, D, 880, might seem preposterous in that context, but that's actually the load that we would use to design this floor space if it was an assembly occupancy. What that means is if it's a theater or a lecture hall, like in C13, or if it was a dance floor. If you were having a party in here, you might not be closely spaced at 6 people per square meter, but people are going to be dancing. There's a lot of jumping up and down. And so there are a lot of reasons why we might design for 880 people, which is an average of about 6 people per square meter. I don't think 5 people want to come up here and join me in this little 3 tile by tile space, so I won't ask that. But oftentimes, we're going to be designing for this load, which is about 2.4 kPa. Sometimes we're going to be designing for that load, which is 4.8 kPa. And it's fun to just get you thinking about that before we get in and start talking about things. Okay, so we talked about things that could be dead loads. We'll talk about how to factor those in. Live loads in general tend to be people and everything that can move. And spaces like this would be designed for something like 3 people per square meter. So we're going to start talking a little bit about dead loads. And again, this is the boring part. I'm going to tell you what I already told you, and that's that the specified dead load for a structural member has to include anything permanently supported by that member. And that includes the self-weight, permanently supported construction materials and equipment, including the weight of other structural members. So a column supports its own self-weight, but it also supports the weights of the joists and the girders and the slabs that are supported by it. Vertical weight of earth, plants, and trees, and partitions. Partitions are non-structural dividers. Most of the time, things like this is a masonry block wall. Shouldn't be grouted, should just be hollow core wall that's put together by masons. Sometimes masonry is load bearing, which means it's a structural wall that supports the weight of joists and roofs. But this is a concrete moment frame structure with a flat slab, and so none of these walls are actually structural. They're just here to divide up the space, right? We need a classroom, want some privacy and some acoustic barrier, so we've got an enclosed space. That's a non-structural divider. Now, some partitions are a little bit weird because sometimes they're pretty permanent, like this wall here. Anyone been in an office building before? Working in an office, get stuck in a cubicle. Those cubicles can move. They sit on the floor. They're kind of furniture, but they're also kind of not furniture because they're more permanent than other kinds of furniture. It's kind of weird to say that. But those kinds of partitions might also typically go under dead loads, despite the fact that you could potentially move them. They're more or less space dividing things, and so even cubicles would tend to get slotted into the partition spot. If you have partitions, the location should be shown on the drawings. And for example, this wall here, there's definitely a concrete beam that sits underneath this wall. That wall needs to be designed to carry the weight of this wall. And so the location of that wall should be specified in the drawings, and the beam needs to be designed to support that entire wall. Where they're not shown, for example, you're designing an office building, you're just designing it, and it's actually going to be the tenants. They're going to come in, they say, we're going to renovate the space and we're going to set up our offices the way that we want to set them up. And sometimes in that case, they're not going to be shown. You can use the anticipated weight. If the architect says, actually, we've got this cool system, it's like half a kPa roughly on average, you can use that for design. But if you don't have any other information, you need a minimum of 1 kPa of dead load in your calculations to consider the weight of these non-structural dividers. When you do it, you have to specify partition weights on the drawings. And so, for example, you might say on the drawings, dead load, partitions equals 1 kPa. Okay, that would be something you would include on the plan drawing for the floor that you're working with. So you might be like floor 3, dead loads include partitions of 1 kPa, structural self-weight plus whatever else the dead weight of the structure might sum up to. Okay, so that has to be shown there. Last thing that's important is that if there's ever a piece of dead load that counteracts, like for example, if it's soil or earth, soil and earth can be dug up and moved quite often. If any of that is helping reduce the moment or shear or axial force on a member, then you need to omit that. We're not going to get into that much in this class, but that's something that's important to think about if you do choose structural engineering as a future career. These are the highlights, right? This is what dead loads are. This is what needs to be considered in terms of partition weights. But don't just take my word for this. Go actually read section 4.1.4. If this was a lecture where I just read that to you, you'd be all sleeping before I even started. So this is an example of what partitions might be. Minimum of 1 kPa, and that's to include all this office space division. Sometimes it's like a timber stud wall or a steel stud wall, drywall, crack filling, maybe it's masonry block wall. Masonry block wall is quite a bit heavier than your typical partition, so sometimes you might go heavier than that. But that's the stuff that is supposed to be considered when we're looking at partition weights for our structures. Does anyone know where this is? Anyone nodding? Yeah, the Kin building, right? I thought this was really cool. I was walking around campus one day just looking for pictures of structural steel to take pictures of. And I walked in the Kin building for the first time. And it's really fascinating because it's the only space on campus where they've got this drop ceiling that actually exposes everything, right? So as an engineer, it's great. You can walk in and you can see the types of stuff that we don't actually see in the structure when we're looking at it. You've got all these pipes, which are probably steam or plumbing or other utility lines. You've got some duct work for air handling that the mechanical engineers would be interested in. You've got fire protection systems, right? Sprinklers for fire. You've got all of the different structural components. And then you've got this fluffy stuff, right? We don't make structural steel buildings out of teddy bears. What's that fluffy stuff you see on that? Does anyone know what that is? Fireproofing. It could be insulation. So on the outside of a wall, it might be, but that's fireproofing. It gets sprayed up there. It's kind of like a cementitious material, and the purpose of the fireproofing there is because we've got an exposed ceiling. Normally, a ceiling like this would be fire rated. So if you've got fire coming up, the ceiling is a barrier to protect the roof from extreme heat. When steel heats up, it gets weak. So we want to protect it from fire. And because it's exposed, they actually had to fireproof it here, right? Because the ceiling's not actually a fire barrier. It's dropped, it's there. It looks like it's there, but it's not actually there in completeness. Does any of this stuff look like a uniformly distributed load to you? We've got ceilings suspended from locations at some spots. I mean, the closest thing might be like the floor. The floor is pretty uniform, and we've got the fireproofing in terms of thickness. It might be relatively uniform. But then we've got like duct. It might be a line load here. And then heavy sprinkler system or plumbing utility, line load there. It's kind of distributed more or less uniformly from the bottom of the ceiling or the bottom of the floor above. But it's not really uniform. Same here. This is actually one of the labs downstairs. There's some more utilities. There's a curtain hanging from the ceiling, very similar to what we saw before. There's a lot of fireproofing, HVAC, lighting, and utilities. That's basically what's suspended from our ceiling. And in this case, again, none of this is uniformly distributed. We've got a pipe that's more or less applying point loads at the places that it has hangers. We've got a duct that might be supported every so often, a couple point loads here and there. We've got a light system that has a point load there. The closest thing here to uniformly distributed load would be the concrete on the top of the floor, maybe the flooring, and the fireproofing on the underside. Okay, so the real loading that we might actually have on a building, we might have something that sort of approximates a uniformly distributed load maybe, and that might come from the concrete, it might come from the fireproofing, it might come from the tiled floor, right? This floor is linoleum. It's pretty much uniformly distributed over the floor area, so that's pretty much uniform. But then every once in a while, you're going to have some pipes that get suspended. Maybe you've got a cable tray with some wires that you're going to suspend over a couple points. And maybe you've got like, I don't know, some kind of mechanical unit that provides cooling capacity. This is not a uniformly distributed load. If we were to try and draw the shear and bending moment diagram for that, that might be interesting. It's not going to be exactly right, but we're going to have some kind of reaction, and then we're going to go down a little bit, and then we're going to have some kind of point load, and we're going to go down, and then down and down and down, down a little bit more, down a lot from the point load, down from the point load, and then up from the reaction. So very quickly, very roughly sketched crappy shear force diagram, but that might be what it looks like. And then we could try to sort of figure out what the moment diagram might look like. It's going to be a little bit harder to draw, but it's going to look something like this, right? So not uniform means our shear force diagram isn't what we said it was before in lab the other day. Moment diagram, that's kind of close, but not exactly right. So what we do here is we say, okay, well, it's not uniform, but I'm going to get a maximum shear somewhere. So on the right-hand side, I've got a maximum shear. And this is not a perfect parabola, but somewhere up here, I have a maximum moment. And I know that the engineer is not going to analyze the joist for roughly uniformly distributed load, a few point loads, because it's not practical. You don't know where all this stuff's going to go, and even if you do, it sometimes changes. So what we do instead is we say, okay, what is this maximum shear force likely to be once we've got plumbing and HVAC and lighting everywhere and all the structural force systems in place? And what is the maximum moment likely to be once we have all those systems in place? And then we say, what is the equivalent uniformly distributed load acting on that joist that would result in similar maximum shear force, Pmax, and they're almost as rough as the rough ones on the right, Mmax. Okay? So this is what's really going on. We're never going to do that kind of analysis. We just want to know what are the maximum effects likely to be, and so we make an equivalent uniformly distributed load that approximates what those maximum actions will be. It simplifies our structural analysis. It makes it easier to tabulate these things, and it makes the design process overall simpler. Okay, does anyone have any questions about this concept of what the loading actually is versus what we're assuming it's going to be from a design perspective? Okay. So where do these come from? Well, some smart people went in and they figured out, well, we actually have to figure out how heavy all this stuff's going to be. It can change more or less, but tile, if you can weigh one tile and it's a foot squared roughly, you can say, okay, a tile weighs this much over 1 foot. The glue that you put down weighs so much over a square foot. If you're tiling something, different plumbers or different tile workers have different amounts of mortar to put down, thin set to set tiles. And so they might actually, in a lab somewhere, build a little floor that measures the weight at the 4 corners, for example. And they'll have someone come in and say, we want you to install this tile. And they'll put the thin set down, they'll install the tile. And when they're done, they'll weigh it. They'll say, okay, the weight of this assembly over a square meter is 0.3 kilonewtons. And all of a sudden, the tile for dead load purposes becomes 0.3 kilonewtons per meter, or 0.3 kPa. Okay, so they do this for a bunch of different stuff, a combination of measuring weights and actually just trying to calculate them based on typical densities over an area. And the handbook on page 769, more or less, the second printing might have a slightly different page than the first printing that I have. But if you've got a certain kind of steel deck, 0.9 to 1.5 millimeter thickness, then there's a certain load in kPa or kilonewtons per meter that's assigned to that. You've got different kinds of flooring, so you've got linoleum, different kind of hardwood for softwood or hardwood floor, carpeting, asphalt concrete, a whole bunch of stuff. Mastic if you're getting really fancy, or terrazzo per 10 millimeters of flooring. So you're going to figure out basically what the architect wants. And say, architect wants this really fancy, heavy mastic flooring. And so in that case, I know they're going to put 20 millimeters down, so I'll use a dead load for that mastic floor of 0.45 kPa. Okay, so it's kind of boring. You go and you find what's supposed to be there, and you kind of add it all up and figure out what your dead load is going to be. So as an example, we might have something that looks like this. And if you were to pull out a section of the ceiling, you might see something like this. You've got some linear lighting systems. You've got some ductwork going through beneath the framing. You've got some plumbing utilities. You've got a steel deck, some concrete floor, some hardwood flooring. It's a fancy office, some lawyers working there maybe. Hardwood floor and some partitions that form cubicle workspaces. And all you do is to say, okay, we're going to separate this out into the different things. We've got partitions, we've got wood floor, we've got concrete slab, we have steel deck, we have steel framing and connections that we're designing. Then we have some mechanical and electrical systems and suspended ceiling. And what you're going to do is you're going to go to page 7-69, and you're going to remember from NBC that we need a minimum of 1 kPa. Architects didn't tell me how much this is going to weigh, and I have no specs from the manufacturer, so I'm going to use 1 kPa. If I go to wood floor, let's just assume it's a hardwood floor. I'm going to come here and I'm going to say, okay, hardwood is 0.08 kilonewtons per 10 millimeters of thickness. Oftentimes these kinds of things, they're like 1/2-inch planks, and so maybe it's 12 millimeters instead. So I would add 20% to that load to get 0.1 kPa, rounding to 2 digits. Maybe I've got a 4-inch concrete slab. It's 100 millimeters thick. I'm going to multiply the weight per 100 millimeters from this table. Concrete per 100 millimeters, I'm going to assume it's normal density concrete. I'm going to take 2.31 and multiply that by 100 millimeters. So I've got 1 worth of 100 millimeters, so 2.31 kPa. I've got steel deck. I'm going to assume, and we're not going to talk much about steel deck in this class, but I'll tell you what you're going to have. Let's just assume it's 1.5 millimeters thick, which is like an 18 gauge steel deck. It's pretty thick. I'm going to come here and I'm going to say, okay, I'm going to go to 776. I'm going to go to 1.52 millimeters thick and take a 0.3 kPa dead load. Mechanical and electrical systems, you just allow 0.25 kPa. That's in the tables. Suspended ceiling, you basically allow 0.2 kPa. The suspended ceiling and all this other stuff is more likely to be where you think it's going to be. Mechanical and electrical systems kind of go wherever, and so it's more of an allowance. You don't actually know where it's going to be, but that should be enough. We're not knowing when we start the design how heavy these beams are, or how heavy the girders are, or how heavy the columns are, right? We don't know what that's going to be. So we can't just include the self-weight of the member is because we haven't picked one yet, right? That's our job, is to pick steel beams and columns. If you don't know what it is, or you can pick something and be like, oh, well, maybe it's going to be this beam. That's not the best thing. The easiest thing to do is just to assume that once you consider the self-weight of the joist and the girder and the columns, just add in about 0.6 kPa, and that should cover you for the structural framing. So all we do here is we sum it up. We get a dead load of 4.76 kPa, and I like to round these things to around 2 digits. So we would say that we design a floor system like this for a dead load of about 4.8 kPa. If this was a live load, 4.8 kPa is that 880 people in here. Okay, so this floor system might weigh 880 people worth of weight, and that's a significant load.
Will we ever round down, like just like normal rounding, or would we always try to round up?
I would round up. I wouldn't round, like, I mean, if it's the 3 significant figures, you just round as you'd round.
4.73, would you round up to like 4.75?
I might just use 4.73. I might use 4.7. I mean, remember, there's some inherent variability here. We're going to try and capture some of that in the load and the factors of safety later on anyway. But if it was 4.73, I might still just round it up to 4.8 because engineers tend to be on the conservative side. It's more than 4.7, and I want to use 4.8. But if you're using like Excel or MathCAD, you're not going to round it anyway. So this is more just like hand calculations. If you're doing hand calculations, 4.8 kPa is much easier, for example, to do calculations with on a slide rule, as you would in the 50s, 60s, maybe part of the 70s, okay? We've got modern tools now. We can do calculations without having to round, but I just like a nice round 4.8 here. I would specify that on the drawings, and I'd use that for a design if it were me. Cool? Cool. So my number is 4.8. How likely is it actually to be 4.8 kPa? That's a number, right? What if the partitions are a little bit lighter or heavier than they were? What if the concrete, like, anyone here pour concrete before? Can you, like, who here can pour a concrete slab to exactly 100 millimeters thick? No one. Yeah, exactly. No one's going to do it. It might be plus or minus quarter inch, half inch, so plus or minus 10 or 12 millimeters. So there's some inherent variability there, right? The construction process has variability. The fabrication process, the thickness might not be 152. The density might not be exactly what it's supposed to be. We already know there's some variability in the geometry of our sections. And the people, the plumbers, the mechanical, electrical systems, they're just going to come in. They're going to go wherever they're going to go. And so there's some inherent variability in these loads, just like we talked about before for the strength perhaps of a tension member. So if I was to plot what people have found to be roughly a probability distribution function that overall, on average, represents the dead loads in our structure, we tend to, or maybe I'll ask you this, so specify dead load. So this is the number. This is our 4.8 kPa. Okay, and the bias they found tends to be about 1.05, variability about 0.1. What does this bias tell us about the 4.8 on average? Do we expect on average the dead load to be higher or lower than what it is that we just calculated on average? So the number we calculated is 4.8. On average, we'd measure something higher. So the ratio of whatever it is to what we've calculated is 1.05, which means on average, 5% we're going to have a dead load that's about 5% higher than we typically would calculate. Dead loads, for the most part, have pretty low variability. Concrete thickness might vary, thin set thickness might vary, density might vary, but it's a pretty low variability. It's higher than the geometric variability of a hot rolled section, for example. The variability for the geometry of a hot rolled section is like 0.001 or 0.0 something. So an order of magnitude more variability. But if we look at this curve here, if this is what we're calculating, we're more likely to overestimate the dead load. And I'll ask this question. Is it better that we overestimate the dead load or underestimate the dead load? Overestimate, right? We don't want to underestimate load. So just from this PDF, we'll see more often than not, we're specified, actually, did I get that right? Underestimating the dead load, right? So more often than not, we're slightly underestimating. Sometimes we're overestimating. And so we need to do something there, and we'll see how we use these statistics later to capture that variability. Live loads. Actually, not much to this. I'm going slower than I typically would, apparently, on this. Members have to be designed for uniform live loads that come from a table, okay, or concentrated live loads from another table. And what's important here is between the point load and the uniform load, we have to design for whatever makes things worse. None of these other things are super important for us here in this class, but the specified uniform loads have to be applied over an entire area, and it has to be applied over areas that generate the worst effect. We're not going to get into that much in this course. Same with concentrated live loads. For the most part, simple framing, we just apply the loads everywhere and we'll figure it out. Concentrated live loads need to be applied in the area that generates the worst effect. If I wanted to make the biggest moment on a beam, where would I apply a point load? In the middle, right? If I wanted to get the biggest shear force from a point load, where would I apply the point load on a beam? Right next to the support, right? So point loads are a bit more complicated. Uniform loads, I mean, they're uniform. You get maximum shear from wherever you apply them. This is where, this is just one part of this table, okay? So go to page 4-9 or PDF page 438 of the building code. These are some values, okay? So if this was an assembly area or an lecture hall, 880 people is 4.8 kPa. Other assembly areas like classroom or courtrooms, 440 people in here, 2.4 kPa. There are some other things like factories. Obviously, there's going to be a lot of heavy stuff. Library stacks, heavy books on tall shelves, 7.2 kPa. We've got an area like that just down the hall. Okay, so the first part here is you need to know what the building is going to be used for. If it's office, that's another assembly area, you're going to pick 2.4. If it's an apartment and a residential space, you're going to pick 1.9. Another thing that's important here, corridors, lobbies, aisleways, 4.8 kPa. So as soon as we walk out this classroom, we're in 4.8 kPa space because everyone's going to leave their classroom back into the hallway. In a fire, for example, more people are going to go there more quickly. That space needs to be designed for more live load. I'm not going to show the tables. They're not particularly important for the concentrated live loads. But what I will show here is roughly how the probability distribution function for the live load tends to compare to that for the dead loads. So do you notice anything immediately about the variability in the live loads here? It's very broad, right? High variability, hard for us to accurately or precisely estimate what the live load is going to be. More variability, we're more likely to overestimate the live load, right? So this is the space where we're overestimating the live load. This is the space where we are underestimating the live load. So that should make us feel good. More often than not, we're overestimating the live load. And despite the fact that we're overestimating it, there is still quite a bit of variability. For example, right, we're overestimating the live load a lot, but if we compare that to the dead load, there's more probability that we're going to underestimate the live load than the dead load, despite the fact that on average, we tend to underestimate our live loads. Variation of live load with tributary area, I had talked about before, specifying or calculating an appropriate live load reduction factor. And I use this example because it's fun, right? We've got an office building. Let's just assume we're looking at the MB Power building downtown. It's also called the BMO building. Depends on where you work and which side of the building you see more often. The floors are 120 feet by 140 feet. There are 9 floors above the ground. It's mostly office space. There are some vaults and stuff, so I'm simplifying a little bit. But if this was a typical office building, we've got 9 floors of office, so we're going to have 2.4 kPa of office space. And so if we use the floor, 120 by 140 in feet is 1,560 square meters. We had the 3 people per square meter, roughly speaking. So 2.4 kPa is about 3 people per meter. How many people do you think are going to be in that building based on the live load calculations that we just did? Well, we've got 3 people per meter squared times 1,560 square meters times 9 floors. And we've got close to the entire population of the city in the NB Power building at one time. Does that make any sense? It doesn't make any sense. It's very likely that at some point if you're in a meeting room or in a corridor, that you're going to have two friends next to you in this square meter space. It's very unlikely that there's also going to be someone over here with two friends in this space, and very unlikely that there's also going to be someone here with two friends in this space all throughout the structure, right? So localized areas or small structural members need to be able to support the full live load. But as we go down, for example, one of these columns has to carry 9 floors of people, and it's just not likely to be there. So what we do here is we use something called a live load reduction factor to account for the fact that it's likely that we're going to have fewer people in the building than we actually do. You don't get to reduce the live load if you have an assembly occupancy or when you're using a minimum live load of 1 kPa on the roof. You do get to if you have members with a tributary area of greater than 80 meters that support things like storage, manufacturing, retail spaces, or garages with a live load of greater than or equal to 4.8 kPa. If you have this situation, then you can calculate a reduction factor that you apply to the shear or live load moment acting on that member. You get 0.5 plus 20 divided by the tributary area of the member you're supporting. Now, if you've got 80 exactly, if you take 80 and plug that in, you're going to get a value of 1. Okay, so I've often been asked, it's 80, do I apply it or not? It's like, well, you can apply it if you want, but you're going to calculate 1 and you're going to waste your time. It's more useful for office spaces, okay, so members with tributary area of more than 20 meters squared, supporting anything else. We get a live load reduction factor of 30% plus the square root of 9.8 over the tributary area for that specific element. When you're applying it, though, you have to specify that on the drawings. You have to say, I'm using a live load reduction factor of 0.6 in designing these members. The reason for that is if someone comes in and they say, okay, I want to renovate and change the occupancy, and someone's trying to determine whether or not the current loading is satisfactory or not, if you don't say there's a live load reduction factor applied to what members, the engineer is going to be like 2.4 kPa times tributary width, WL squared over 8, not good. Okay, so you have to specify the live load reduction factor that you're using on the structural drawings. So if you want to just kind of figure out what's going on here, here's a simple flow chart to help you navigate that. Is the occupancy assembly or similar? And what I mean by that is it includes retail and other areas. So you have to be familiar about what that box means. If yes, am I designing for a live load of 4.8 kPa or more? If not, no reduction. If yes, is the tributary area for my member more than 80 meters squared? If not, no reduction. If yes, I can calculate the reduction factor using 4.1.5.8. If it's not assembly or similar, is the tributary area greater than 20 meters squared? If not, no reduction. If yes, you can reduce it using 4.1.5.8, sentence 4. Okay, so to give you a sense for what that looks like, if I was to plot these with tributary area, so as the tributary area goes up, live load reduction factor expectedly goes down. The bigger the area, the less likely the full live load is going to be over the entire area. And so for really small areas, you don't get any advantage. For the most part, practically speaking, office spaces, your columns might get down to about 0.4. For other kinds of buildings, you might get down to about 0.7. Usually, in my experience, the live load reduction factor for a lot of columns tends to be about 0.5. For the girders, you might even get something like 0.9 or 0.8. For joists, you tend to rarely get any advantage from this live load reduction factor. Okay, so a quick, oh shit, I did not, that's okay. I don't think they got the answer right anyway. So take what we just talked about. If you have the slides, you can use the flow chart. In this classroom now, we are designing this floor, for example. Let's say this is a building that hasn't been built yet. Would you use a live load reduction factor to perhaps support any of the elements that are supporting the floor? And there are some answers. Yes, I would use it for all members. No, I wouldn't get to use it at all. Yes, but only for members with tributary areas greater than 20 square meters. And I always love to put an I'm not sure box in there so you can always participate and make it sure that you have no idea what I'm telling you and I need to change how I explain things. at least try to open up the the little floor area. Think about some of the things that we've talked about. I definitely don't want it to just be a default box. So we're reaching a state of more or less equilibrium here. And I'm not going to go through every single answer, but I do want to highlight what I think I remember as the right answer. The right answer here is B. We do not get to apply a live load reduction factor. Does anyone who picked B want to share why they picked B if it wasn't a random selection of sorts? Anyone confident in B and why they picked the answer? Silence. That's okay. The first step here is, do we have an assembly area or similar? And I think perhaps I might not have detailed this out as well as I needed to. But if you go back to slide 19, we basically have two categories of assembly area. And if you go to the building code, it'll say what's assembly and what's not. But classrooms are considered another assembly area. Okay, so this is an assembly area. Of course, you assemble here to listen to me drone on for an hour, and then someone else for an hour, and someone else for an hour. And so this is an assembly space. Okay, classrooms are an assembly area. Is the live load greater than or equal to 4.8 kPa? Well, no. For classrooms, we designed for 2.4 kPa. And so this is an assembly space that doesn't have a live load that's big enough for us to apply confidently a live load reduction factor. And so that means no, we do not get to apply a live load reduction factor. Okay. Any questions about that problem and what steps you need to go through to figure out whether or not you could or could not apply a live load reduction factor? We've got a few minutes to go through a quick example. This one is asking us to determine whether or not we can apply a live load reduction factor to the girder that's in bold and red right in the middle of the floor plan there. And if it can be reduced, we want to calculate the live load reduction factor for it. And we're not going to get to the shear and bending moments on the girder here. I'll extend that example in the example notes that are posted to the course website. What we'll do, though, is we'll figure out, can we apply live load reduction factor? And from there, we'll determine what the live load reduction factor would be. Okay, so we have an office building, 2.4 kPa. Let's go to our flow chart. We need to determine first, is office space an assembly area or similar? Now, if you go to the building code, this is not what the table looks like there, but these are the only categories of assembly area. Offices above the ground level are not assembly. This is everything else that's not considered an assembly space. So office space is not an assembly occupancy. So we go down immediately to here. And the next step is the tributary area for the member that we're looking at bigger than 20 meters squared or not? So what we need to do is look at this girder and figure out what the tributary area for the girder is. That means we need to go back to lecture 3, right? We know we've got these 6 joists framing into the girder. So if we look at the tributary area for a single joist, right? That's the length of the joist times the tributary width for the joist. We've got that at 6 locations. Half of that joist area loads the girder. We've got another half of a joist loading the girder, another half of the joist loading a girder, another half of the joist loading the girder, and 2 more halves of joists loading the girder. Tributary area is the area of floor that the structural member is responsible for supporting. This girder is responsible for supporting the load from half of 6 joists. And so the tributary area here is half of the tributary area for the 6 joists.